Welcome to the class. In the last class we had seen how to find out the basic performance parameter like efficiency in case of a turbine stage where we had considered one nozzle and one row of the blades. There we found out that for the nozzle plus blade combination we will get the optimum efficiency, maximum efficiency as cos square alpha, and that efficiency would be at a particular velocity ratio which is cos alpha by 4. So, now we will see the rest of the things. In the turbine, as we know that we have nozzle and a blade. This is a stage of the turbine. Now, if we have very large pressure in the nozzle at the entry to the nozzle in the boiler and very low pressure at the exit of the turbine, that is in the condenser, then we need to have complete expansion in the nozzle and then complete work extraction has to be done by the blades. So, with this fact we have to work. However, it is not logical. We will see that if we have only one row of nozzle and only one row of blades, then it constitutes a stage of a turbine as what shown in the figure. But if we have complete pressure drop, then in the nozzle whatever the pressure drop which should take place between the boiler and the condenser, then we will get very large velocity at the exit of the nozzle. So, here we will have very large velocity, absolute velocity V1. Then as what we have seen, there is a particular relation between absolute velocity at the exit of the nozzle and the blade for getting the maximum efficiency. So, it turns out that there is very large velocity of the blades as well. So, the large velocity of blade, we know that Vb is equal to pi dm into n by 60. So, we get very large velocity of Vb. If we are going to obtain the complete extraction through only one stage, then this Vb will be large. So, this large Vb can be accommodated by two facts: either we should have very large n, or which we should have very large dm, which is the mean diameter of the blade. But if we have very large n to accommodate the complete Vb, large Vb, then we should have fixed diameter dm, and large value of n introduces large centrifugal stresses and very large friction in the bearing. So, we will have large frictional loss and we will have large centrifugal stress. So, further if we fix the speed and if we change the dm, then it turns out that we need very large diameter, mean diameter of the blade. So, that also creates a problem. So, further there would be problem that we will have further very large velocity V2 at the exit of the complete stage. So, we would not able to completely extract the expected energy from the stage. So, this tells us a fact that it is not good idea to have only one stage of a nozzle and blade combination. We should have multiple stages, and then that combination is called as compounding. So, we should not have complete enthalpy drop in only one stage. We should have enthalpy drop in the multiple stages, or we should have the not complete velocity extraction in one stage. We should have velocity extraction or kinetic energy extraction into multiple stages, and such facts are called as compounding of steam turbine. So, we will see. So, steam is allowed to expand over large number of stages so as to have reduced turbine speed or desired dimension of the rotor. So, very first method of compounding is pressure compounding or called as Rathod staging. So, here as what we see that there will be multiple nozzles and multiple blades. So, one nozzle would lead to some enthalpy drop in it and creates corresponding kinetic energy. That kinetic energy will be extracted by the blades and then we will have certain else or remaining kinetic energy change or remaining enthalpy drop and corresponding rise in kinetic energy in the next nozzle, and then corresponding blade will extract that kinetic energy into the work done. So, we have multiple nozzle and blade combinations, or we have multiple stages in case of pressure or Rathod staging. Here we are calling it as pressure compounding, since not complete enthalpy drop or pressure drop will take place in the one nozzle, but we will have multiple nozzles in the stack. Further, each blade will not have any static enthalpy drop, or each blade will not have any relative velocity change here. So, this is what we will have a staging called as pressure compounding. So, as what expected, we said that one nozzle will rise the velocity and drop the pressure and drop the enthalpy, and then it will go over the moving blade, then next it will go to the next set of nozzles, next set of nozzle will further rise the velocity, drop the pressure, then it will go over the next or second set of nozzles, and it will continue. So, this figure is for 3 staging, this figure is for 2 staging. And as what we have said, we have some pressure drop in the first nozzle, then we will not have any pressure drop in the moving blades, then in the nozzle we will have a pressure drop, and then again in the second set of moving blades there is no pressure drop, and this will continue. Similarly, velocity rise will take place in the nozzle across the pressure drop or enthalpy drop, and then this kinetic energy will be extracted by the nozzle. Here remember that we are talking about the extraction of absolute kinetic energy, but when we are telling that the impulse turbines are there, then there is no change in relative velocity, or what we have seen that if at all there is change in the relative velocity, that is mainly due to friction, and we have said that there is a blade friction factor, and this will continue into the rest of the stages. So, such staging is called as pressure compounding. So, we can see the TS diagram or HS diagram for the pressure compounding. We know this is the boiler and then this is the condenser. So, in the first stage we will have first enthalpy drop in the nozzle. So, this is the nozzle enthalpy drop, and then we have at this point only we have the rotor. Since the rotor will not have the enthalpy drop, then second nozzle will have second enthalpy drop, then this is the second rotor, then we have third enthalpy drop, third rotor, and fourth enthalpy drop and fourth blade. So, this is the complete expansion from 0 to 4 in the 4 stage pressure compounding turbine. Now, we can see that velocity for single stage, as what we know, can be found out from this formula, which is V1 into 44.72 square root of H naught minus H4 into nozzle. So, this is if we have only one stage, then we would have this as the absolute velocity, but now we have 4 stages. So, we should have this enthalpy drop is divided into 4 parts. So, this enthalpy drop into 1 by 4 into nozzle efficiency square root 44.72 is the first velocity or velocity at the exit of first nozzle. If we would have 3 stages, then this 4 would be replaced by 3. So, enthalpy drop in one stage is equal to total enthalpy drop divided by number of stages. So, we basically have in our formula V1 is equal to 44.72 into delta H stage into nozzle efficiency. So, this is ideal enthalpy drop in a stage. So, if we can find out enthalpy drop in one stage, then we can find out velocity at the exit of the first nozzle or corresponding stage nozzle. So, if we know enthalpy drop in one stage and if we know total enthalpy drop required, then we can also find out number of stages. So, number of stages is equal to enthalpy drop total divided by stage enthalpy drop. So, this is all about the pressure compounding or Rathod staging. Now, we will see next staging is called as Curtis staging or velocity compounding. This is a second type by which we can reduce the dimension of the constructional dimensions of the nozzle, or we can have basically lower speed. So, in case of velocity compounding, we will have first nozzle which will actually completely expand the steam from boiler pressure to condenser pressure. It is very important. In case of pressure compounding, we were not completely expanding the flow of the steam, but we were partially expanding in multiple nozzles. We were having partial pressure drop in multiple nozzle, but in case of Curtis staging or velocity compounding, we will have complete enthalpy drop into the nozzle, and then we will have the moving blades where partially we will have the work done or partial extraction of kinetic energy. Then the next set of blades are called as stationary blades, or they are also called as guide vanes, where they will guide the flow to the next moving blades. In these guide vanes or stationary blades, there will not be any enthalpy drop, or there is no in ideal case there is no velocity change. Then further moving blades will change the kinetic energy of the flow. So, here we will have velocity compounding will have complete enthalpy drop in the one nozzle, and partial kinetic energy change will take place into the multiple rotors. So, such turbine is called as Curtis staging. As what we can see into this two stage Curtis turbine, there is a nozzle, which this is a nozzle where we will have complete enthalpy drop or complete pressure drop, and then in the moving blades, when we go to the moving blade in the same nozzle rather, we will first have velocity rise, and this velocity rise will be decreased in one set of one set of moving blade, and then into the fixed blades or guide vane there is no change in velocity, and in next set of moving blades we have rest of the change in kinetic energy. So, we will have change in speed. So, pressure drop has taken place completely from the boiler pressure to the condenser pressure in the one nozzle, but the fixed blades are just the guide vanes. So, they are changing the direction of absolute velocity. The fixed blades or the guide vanes, they are just changing the velocity, but we will have kinetic energy change into the moving blades partially. So, one set of moving blade is changing the absolute velocity, and then second set of moving blade is changing the rest of the kinetic energy. So, it is only velocity change is taking place into the moving blades, and we have this fixed blades as only the stationary, we have fixed blades as the guide vanes. So, let us see how would it proceed. So, as what we have seen, this is a two stage Curtis turbine. We have nozzle here, and then in the nozzle we will have complete enthalpy drop and maximum velocity at the exit of the nozzle. Then there will be blades, and these moving blades will change the absolute velocity to some value at the exit. Then there will be stationary blades or guide vanes. They will change the direction of velocity such that it will be smooth at the entry to the second moving blades, and then in the second moving blades we will have rest of the velocity change taking place. So, if we see the velocity diagram, then for the first set of moving blade, this is first set of the moving blades, and this is second set of moving blades. For the first set of moving blades, this is the absolute velocity, very large in magnitude at the entry, and this absolute velocity has angle alpha 1, and then we know that the moving blades are rotating with velocity Vb, tangential speed Vb, and they are rotating with speed rpm n, then there is an angle alpha 1 between them. So, we have relative velocity at the entry as Vr1 and corresponding angle as our beta 1, but while going out from the first set of moving blades, the blade will have absolute velocity V2 and it will have relative velocity Vr2. Here we are drawing this diagram for the fact that the alpha 2 or delta is greater than 90. This angle is greater than 90 degree, and here we are saying that blades are not symmetric, or blades may be symmetric where beta 1 and beta 2 can be accordingly adjusted, but at this stage we are saying that Vr1 is not equal to Vr2, and so there is mismatch in magnitude due to friction factor. Now, the second stage of moving blade, this same V2 will be here as V3. Now, if there is frictional loss between the while the flow is taking place on the stationary blades or the guide vanes, then V3 will be less than V2, and we can again say that V3 upon V2 is equal to Kb, which is a friction factor. So, V3 is there, and then we have second angle as alpha 2 for the moving blades, and then we have same Vb as the tangential speed for the second stage for the second set of moving blades, and then we so have Vr3. So, here what we are trying to say is this way: we are having nozzle. So, nozzle has 0 at the starting point nomenclature, and then at the exit of the nozzle we are saying 1. Then we are having moving blades. At the exit of the first set of moving blades we are saying 2. Then we have fixed blades. At the exit of the fixed blades we are saying 3, and we are in the second set of moving blades we are saying 4. And present velocity diagram for first set of moving blade is here, and second set of moving blade is here. So, for the first set of moving blades, entry velocity is V1, exit velocity is V2. For second set of moving blades, entry velocity is V3 and exit velocity is V4, since 2 to 3 change is happened in the fixed set of blades. So, we are drawing the same velocity diagram, but here while drawing the velocity diagram, we have drawn this special velocity diagram for the fact that we have alpha 3 is basically less than, basically we have here alpha 3 and alpha 4, which is the absolute velocity angle at the exit, which is less than 90 degree, for which we have drawn this diagram. Now, let us go and see the same velocity diagram we can draw, and we can as well draw this diagram by a new method where we have this Vb inlet velocity triangle, we have inlet velocity triangle V1, we have angle alpha 1, then we have Vr1 as the velocity, relative velocity at the entry. So, this is inlet velocity triangle. Now, we know that there is some fraction by which Vr1 will be reduced to Vr2. So, we will reduce that magnitude, and then now this becomes Vr2 or Vr2 for us. Now, this Vr2 will have, suppose, same angle for a symmetrical blading case. So, we have beta 2 and beta 1 same, and then we have so V2 as the absolute velocity with angle alpha 2. But here while drawing diagram we have to keep one thing in mind, that V1 has direction downward, B1 has direction towards the right. So, VR1 has direction towards downward, but here we have to keep in mind that VB cannot change its direction, it is still in positive x direction or right hand side, but VR2 is in opposite direction and V2 is also in opposite direction. This diagram helps us to, such diagram helps us to simplify the complicacy in drawing the diagram which is conventionally otherwise would be drawn for the fact that symmetrical bleeds and for the further derivations. So, now we can make use of this diagram for finding out thrust and power calculations or for doing thrust and power calculations. So, we know that tangential thrust is equal to m dot into sigma I is equal to 1 to n, and this is for number of stages. So, this is VB into delta VW I, VB into delta VW I. So, this is delta VW I, that is thrust, total thrust or total axial force or torque. Now, we know that power is equal to m dot into VB into sigma I is equal to 1 to n delta VW I, delta VW I. Okay. So, we will have here for two stage power is equal to m dot into VB into delta VW1 plus delta VW2. We have defined VW as the tangential velocity and delta VW means change in tangential velocity. So, that thrust is force which is change in angular momentum or change in tangential momentum. Okay. So, this is the formula for us. So, we can define efficiency or diagram efficiency or blade efficiency is, so for two stage m dot VB into delta VW1 plus delta VW2. For this particular case of two stage we have of m dot V1 square. So, m dot would cancel. So, blade efficiency or diagram efficiency is 2 into VB into delta VW1 plus delta VW2 divided by, so 2 is taken up. So, we will have in general blade efficiency, okay, we will have divided by V1 square. So, we will have efficiency is equal to 2 VB upon V1 square into sigma delta VWI, where I is equal to 1 to n. So, this is what our formula for efficiency. Now, we can find out same way what we did in earlier case, and we can find out the extraction of the work in each stage in proportion with each other. So, now let us draw the velocity diagram for two stage Curtis turbine with frictionless blade and axial discharge. There are two terms over here. One term says that we have frictionless blades. So, if the blades are frictionless, that means we are considering that VR2 is equal to VR1 or VR3 is equal to VR4, and similarly V2 is equal to V3. This is also we are saying. So, velocity at the exit of the first moving blades is equal to velocity at the exit of the first stationary blades. So, stationary blade is not changing any velocity. So, for this particular case, this is the velocity diagram where we will have the VR1 is equal to VR2. Now as per our notation we will have this angle as alpha 1 and symmetrical blades lead to beta 1 is equal to beta 2 and then this angle is equal to alpha 3. So we can find out effectiveness of the moving blade. So as per the formula for work done we need basically delta VW1 for 2 stage it is we need sigma I is equal to 1 to 2 delta VWI and it is equal to delta VW1 plus delta VW2, and for us we know that this sigma delta VWI where I is equal to 1 to 2 delta VW1 is tangential velocity at the entry, and that is at the inlet we have V1 cos alpha 1 and at the exit we have V2 cos alpha 2, but V2 cos alpha 2 is in the, since we are considering delta or this angle alpha 2 as more than 90, so it will be V2 cos alpha 2, okay, plus V3 cos alpha 3 plus V4 cos alpha 4. Now we know V1 cos alpha 1 from this diagram is equal to 4 VB. Each this line corresponds to VB. So V1 cos alpha 1 is a complete AB. Basically this is equal to AB. Since V1 cos alpha 1 is AB, we know AB is equal to 4 VB. So V1 cos alpha 1 is equal to AB and AB is equal to 4 VB. Then we know V2 cos alpha 2 is equal to V2 cos alpha 2 is here and alpha 2 and alpha 3 are same. So it is dA and dA is equal to twice VB. Similarly, we know that V4 cos alpha 4 is equal to 0 since we are considering axial discharge. So there is the angle between the absolute velocity at the outlet and the tangential speed are 0. So we will have this delta VWI sigma I is equal to 1 to n is equal to 4 VB plus 2 VB plus 2 VB, 4 VB plus 2 VB plus 2 VB. So we will have sigma I is equal, this is for the first stage and this is for the second stage, delta VWI is equal to 6 VB plus twice VB. Here now we can see that this is corresponding to the first stage and this is corresponding to the second stage. Now if I want to find out isolatedly the work done for the first stage, then work done or P power for the first stage, I will write down, suppose WD work done for the first stage is m dot into VB into delta VW1, and this turns out to be m dot into VB into 6 VB. So for the second stage or second rotor blade, we are not saying second stage, we are saying that for the second moving blade or practically the second stage of Curtis turbine, we will have m dot into VB into delta VW2 is equal to m dot into VB into twice VB. Now if we take ratio, then VD1 as to WD1 as to WD2 is equal to 6 as to 2, or we will have it as 3 as to 1. So, first stage of the Curtis turbine does basically 3/4 of the work, and second stage does 1/4 of the work. So, total work is 4, like 3 plus 1, but out of 3 plus 1, 3 units of the work is done by the first moving blades and 1 unit of the work is done by the second unit of the blade. Now, if we would have, instead of 2 stages, if we would have 3 stages, then we can prove that WD1 into WD2 plus WD3 is 5 as to 3 as to 1. So, there is total 9 unit of the work. Out of 9 unit of the work, 5 units of the work will be done by the first stage, 3 units will be done by the second stage, and only 1 unit of the work will be done by the third stage. So, only 1/9 of the work will be done in the third stage. So, we do not have to have too many stages in the Curtis turbine. Now, we will go ahead and see that what is the formula for optimum velocity ratio for Curtis turbine. So, let us draw velocity diagram for Curtis turbine again, and in this case we are not drawing the diagram for radial exit, but we are saying that we are not drawing the diagram for axial outlet, we are saying that it is non-axial discharge. But here still the diagram corresponds to the fact that the blades are symmetric and there is no friction. So, we have ideal blades. So, this is alpha 3 and this is alpha 4. So, for this fact we know now how to write down the formula for total work done, which is WD is equal to m dot into VB into sigma I is equal to 1 to 2 into delta VWI. So, we have WD is equal to m dot into VB into V delta VW1 plus delta VW2, but here we can know that delta VW1 and delta VW2 can be found out in this case, where we can write down the formula for delta VW1. Now, delta VW1 is equal to V1 cos alpha 1 plus V2 cos alpha 2, and V2 cos alpha 2, basically V2 cos alpha 2 is this part for us, this is V2. So, V2 cos alpha 2 is practically this big length from here to here. So, if we name A, B, C, D, E and F, then V1 cos alpha is practically for us V1 cos alpha 1 is equal to, we will write down here V1 cos alpha 1 is equal to A into F, but V2 cos alpha 2 is equal to BF, AF plus BF. So, the distance AB is equal to BC is equal to CD is equal to DE is equal to VB. So, looking at that, we know delta VW1 is equal to V1 cos alpha 1 plus V1 cos alpha 1 minus VB. So, delta VW1 is equal to twice V1 cos alpha 1 minus VB. Similarly, we can write down delta VW2, and delta VW2 is equal to V3 cos alpha 3 plus V4 cos alpha 4, and V3 cos alpha 3 is equal to, we can write down now here, V3 cos of alpha 3 is equal to V1 cos alpha 1 minus, but basically V3 cos alpha 3 is equal to Cf, and it is equal to V1 cos alpha 1 minus twice Vb, and V4 cos alpha 4 is equal to V1 is equal to basically Ef, and Ef is equal to V1 cos alpha 1 minus 4 Vb. Okay, so we can write down delta Vw2 is equal to V1 cos alpha 1 minus twice Vb plus V1 cos alpha 1 minus 4 Vb. So, delta Vw2 is equal to twice V1 cos alpha 1 minus 6 Vb. So, we can use this in and write down the formula for Wd, and it becomes m dot into Vb into, for the first stage we have twice V1 cos alpha 1 minus Vb, and for the second stage we have twice V1 cos alpha 1 minus 6 Vb, and then bracket complete. So, we have Wd is equal to m dot Vb into, we have 4 V1 cos alpha 1 minus 7 Vb. Now, let us see the optimum condition for the two-stage Curtis turbine. So, here we are again drawing the same velocity diagram as what we drew earlier, but here while drawing this we are not considering the axial discharge, we are considering non-axial discharge, but we are still considering the blades to be symmetrical. Here we have alpha 1, here we have alpha 2, here basically here equal to alpha 3, and then we have alpha 4. Let us name them as A, B, C, D, E, and then I will name this part as F. Now, let us find out various quantities for this first, and our objective is to work out for optimum velocity ratio for Curtis turbine. The reason is as follows. We know that total work done is equal to m dot into Vb into sigma I is equal to 1 to 2 delta Vwi. So, work done is equal to m dot into Vb into delta Vw1 plus delta Vw2. Now, let us find out delta Vw1 and delta Vw2. So, we are interested in finding out delta Vw1. We know that, let us name this as equation number 1. We know delta Vw1 is equal to V1 cos alpha 1 plus V2 cos alpha 2. As per this diagram, V1 cos alpha 1 is equal to A into F, rather AF, and this is equal to, further we know that V2 cos alpha 2 is equal to CF. So, V2 cos alpha 2 is equal to Cf is equal to V1 cos alpha 1 minus twice Vb, and this would be useful to find out delta VW1. Further, delta VW2 is equal to V2 cos alpha 2, or we will have V3 cos alpha 3 plus V4 cos alpha 4. Here V3 cos alpha 3 is equal to, as per this diagram, we have again equal to Cf, and that is V1 cos alpha 1 minus twice Vb, and V4 cos alpha 4 is equal to Ef, and then that is V1 cos alpha 1 minus 4Vb. Since as per this diagram we will have AB is equal to BC is equal to CD is equal to DE is equal to VB. In this we can put everything into equation number 1. Now we can put all these equations into equation number 1, and then we can write m dot into Vb into delta Vw1, and then this is V1 cos alpha 1 minus plus V1 cos alpha 1 minus twice Vb. This is for first stage, and for second stage we have V1 cos alpha 1 minus twice Vb plus V1 cos alpha 1 minus 4Vb, bracket complete. So we have Wd is equal to m dot into Vb, and then we will have for the first stage twice V1 cos alpha 1 minus twice Vb, and then for second stage we have twice V1 cos alpha 1 minus 6 Vb minus 6 Vb. So we will have Wd is equal to m dot into Vb into 4 V1 cos alpha 1 minus 8 Vb. So we have Wd is equal to m dot into Vb, and then we can take 4 common, and then we will have V1 cos alpha 1 minus twice Vb. Then we can use this for our derivation of efficiency. So let us find out the formula for efficiency, and then we know formula for efficiency is Wd efficiency, diagram efficiency is Wd upon half m dot V1 square. So we have diagram efficiency as twice Vb into m dot into, so these two will go up, so we will have m dot into 4 into V1 cos alpha 1 minus twice Vb divided by V1 square, and m dot will get cancelled. So we have diagram efficiency as twice Vb into m. We basically have 8 Vb. We will write down as twice Vb, and then this would help us later on for 4 into V1 cos alpha 1 minus twice Vb divided by V1 square. Now let us say that rho is equal to Vb upon V1. So we have diagram efficiency is equal to, we will make it a point here, Vb upon V1. One V1 is given here and other V1 we will keep it for inside. So V1 cos alpha 1 divided by V1 minus twice Vb upon V1. So we have diagram efficiency as twice rho into 4 into cos alpha 1 minus twice rho. Now we know for given alpha 1 diagram efficiency is just function of rho, and then if we differentiate it with rho and equate it to 0, we will get a formula as 8 cos of alpha 1 minus 32 rho is equal to 0, and then this leads to the fact that rho is equal to cos alpha by 4, and then this formula if we put into the efficiency, which is this, then we get diagram efficiency as cos square alpha. So we have seen that in earlier case when we were having pressure compounding or only one stage of nozzle and moving blades, then we got optimum efficiency or maximum efficiency at optimum rho at cos alpha by 2, but now we are getting it at cos alpha by 4, but the maximum efficiency is same, which is cos square alpha. This all discussion was about impulse turbine. The next set of turbine, which is reaction turbine, we will see in the next class. Thank you.